So for the talk today, I picked a paper that we're currently working on, so that we're currently revising. So that's what I would like to share the ideas of this paper with you and see what suggestions you would have for us, right? So it's a bit atypical in the sense that we're going to do a paper where we will sort of try to bridge or to combine ideas from pricing and reserving into the same model setting. So it's not purely a pricing paper, it's neither purely a reserving paper, it's one that tries to bridge these two key actuarial tasks, let's say. That's what we try to do, and it's going to be in the non-life field as the topic of today's session is about. This is, well, some ongoing work, as I said, with Jonas Kreviker, who did his PhD together with me, and who's now working at the University of Hasselt as a data scientist. And we teamed up for this project with two actuaries from the Belgian office of QBE Re. So we're going to do a case study in reinsurance towards the end of today's talk. And these two actuaries are Stan and Alexandra. I couldn't find a picture of Stan. And my boys at home, they're, well, in Belgium it's the Lego Masters, at least in Flanders at this moment. So here is the minifig of what an actuary could look like, I guess. So the paper is on arXiv. That is a first version, so I think we have many things to do still and to improve, but okay, we have a draft out there if you're interested in that. Oops. So just to set the scene for today, so today is the non-life insurance thematic day of the conference, let's say. So let's picture the arrival of claims and the development of claims over time with this kind of Lexis-inspired diagram. So we have insured events arriving over time. They will get reported to the insurance company. So that is the symbol here to represent that reporting. Some development of the claim will take place until the claim closes, right? And if we put ourselves at a certain point in time, then we could say that the reserving actuary will look at aiming to estimate or to predict how much capital will be needed in order to fulfill the liabilities of the company with respect to claims that arrived in the past, so that arrived in past exposure periods, claims which have been reported already, like this one, claim event B, claims that have been reported already but are not yet settled. The typical RBNS setting, reported but not settled, but also claims that occurred already but are not even yet reported to the insurance company, so the IBNR problem. So that's what we do in reserving, but of course if we focus or if we look at pricing, then we aim to assess how many claims or how many events do we expect to arrive in future exposure periods, right? And how do we establish an estimate on the frequency, an estimate on the severity of those events in order to do some technical pricing, right? So I take this graph just to remind you of what that reserving and pricing job or task would be about. Now, let's start with a few ideas from non-life insurance pricing, and I'm sure that many of the colleagues today will continue along some of the themes that I have on the slides right now. So the way how I build up the talk is just quickly glance at pricing first, then reserving, and then try to bring these two things together in that case study from reinsurance. So that's how I build up the presentation for today. I guess I should point here. Yeah, okay. I have a tendency to point the pointer like that. I'm just wondering, is the mic okay, or should I? Yeah, it's working? Okay. So we know if we look at the basics of non-life pricing, we look at, say, a policy I throughout a certain period of time, the exposure to risk. We're going to look at, what is the number of claims filed during that exposure period, and what is the total loss amount that corresponds or that will correspond to these reported claims. And if you look at technical pricing models and a frequency severity decomposition, as I have it here on the slide, then the pricing actuary will try to assess with a frequency predictive model, with a severity predictive model, what the technical price or the pure premium for that policy or that policyholder I should look like, right? So we try to make an assessment about how many claims do we expect to happen over a future exposure period, and for those claims that happen, what do we think will be the average what will be the average impact, financial impact of those events? And of course, we know in the literature that there is a lot of work going on seeing, how can we build meaningful predictive models to do that prediction of the frequency and the severity as a function of certain risk factors, right? So that's the basic of pricing. I think my slides are a bit too heavy or too slow. And of course, with the team in Leuven, we try to contribute on that field of technical pricing, and you see a few hints here towards articles that we recently have been able to look into, as going from how do you handle postal codes, or how do you handle continuous risk factors, to do up to tree-based machine learning methods for frequency severity. And then in the last paper there in IME, we focused on some telematics dynamic pricing, right? So we have these ideas out there, and many people. So I put too much pictures in the slide or something. So we know that some of the topics, and I included that just to give you an overview of a few topics in the field there. We have contributions on how to do clever feature selection or feature processing, how to extend our actuarial toolkits of GLMs by looking into more machine learning methods for frequency and severity, and you see, of course, a few ideas of what people have been doing recently or are doing in this field, right? And I think Arthur will continue with talking about things like interpretation, fairness in these pricing models. So these are a few main topics which are currently being covered in that field of actuarial pricing for non-life insurance. Now, the reason why I mentioned these contributions is because the idea that I will try to work on in this paper with Jonas, Stijn, and Alexandre is, if you look at these pricing models, or if you look at these pricing papers in the literature, we're going to assume there that we have, let's say, a nice, if I can put it like that, a nice, complete historical data set with our policyholders, the number of claims they reported during a specific period of time, and then the corresponding severities for building our predictive models on, right? So we're going to assume there that we do that pricing literature with a sort of complete, nice historical data set at our disposal. And that makes sense, of course, and that's nice to do. But what if we don't have such a complete data set yet? So what if the number of claims reported per policyholder, what if some claims are still missing because of that delay between the occurrence of the event and the reporting of the event to the insurance company? And what if some information on the ultimate claim sizes of individual claims, what if that is missing? So what if some individual claim sizes are right-censored because the claim has not settled yet? So if you're facing a data set with that kind of incompleteness, so underreporting of the number of claims on the one hand, and then some right-censored claim sizes on the other hand, so what can you do then as a pricing actuary? So what are a few ideas to do there? You can ignore the incomplete or the part of the information that is missing, or you can do some kind of pre-processing, some ad hoc pre-processing, or some more clever pre-processing before building your pricing models. And then you may say, yeah, Katrien, but maybe that's not too important, or that's not so relevant to consider. But of course, if you think about a reinsurance case study, where there can be a lot of delay in the reporting, and where it can take a very long time for claims to settle, then of course these two problems become more prominent when you have to price reinsurance contracts on this kind of data set with incomplete, missing information. So that's the idea, or that's the part in the literature where we try to contribute with this paper. So what if you have to do pricing, but you're facing this kind of incomplete information in your pricing data set, okay? Maybe I can. This one? Yeah. Okay. I'll do it like this. Yeah. So if we see what pricing actually is, or at least if we talk to some people in the field, let's say, what kind of steps can we undertake then? Well, if you look at the frequency, so maybe some claims are missing because they are not yet reported, we may simply ignore these unreported claims, right, when building our pricing models. And if we look at the severity part, we may either focus on only the settled claims, or we may do some kind of ad hoc best estimate. So we may replace the future development of the open claims either with zero or with some best estimate that we can put together using, for instance, a chain ladder technique or something, tools that we know from reserving. So that's one thing. But then, of course, if you think, okay, I went through this pre-processing, so I completed my data set, for instance, by replacing the right-censored severities with a best estimate. What the pricing actuary then typically will do is take that data set and use it as if it were actual observations, right? And calibrate a frequency, a severity model for technical pricing using these pre-processed, using these completed data sets. So that's also one of the things we want to investigate in this paper. What is the impact of doing that? So what is the impact of calibrating your severity models for pricing on these completed best estimates, treating them in the same way as the actual complete observations that you have in your data set. So you will see that idea coming back later on in this talk. So that was my intro on pricing. So I'm very sure that other esteemed colleagues in the room will continue along these ideas later on. But for me, the point was, yeah, what if the data set that we have is not so clean, not so nice, and what if there's some missing parts there? How do we handle that? So as my title announced, I'm going to bridge the ideas or try to bridge or bring together ideas from pricing and reserving. So let's take a look now at the reserving field and what we can get from there, right? So we know that if you look at the problem of non-life insurance reserving, it's about the development of claims over time. We have the main events here on a non-life claims development sketched on the left-hand side. We have the occurrence of the event, the reporting, some payments until settlement. We know that story, and okay, I've been trying to work on that, on this idea in a couple of papers. And we also know that traditionally, we aggregate that information along some arrival and development direction, time direction, let's say, into a runoff triangle, and we can use that triangle to aim to predict the lower triangle and to obtain as such an estimate for the future liabilities with respect to the claims that happened in the past, right? So we know that story, that's typically covered in non-life insurance reserving. Now, the idea that I want to launch here today, and which will be relevant then for the rest of my talk, is we've seen, of course, in a series of papers in this field, that we can question the way how we use the data for reserving. And with Jonas, we try to distinguish here in sort of three different areas. If you want to look at this literature, what we call aggregate reserving, granular reserving, and individual reserving. So with aggregate reserving, I have the very traditional, let's say, chain ladder or GLM kind of framework in mind, where we do the aggregation into a runoff triangle, but where the periods of discretization are quite large, let's say a quarter or half a year or a year or something. So you see that in the picture. So it's a runoff triangle, but the discretization is quite rough, let's say. What do we mean then with granular reserving? Well, then we say we still do the compression of the data, so the aggregation, but we do it in discretization steps which are quite granular. And in some of our work on IBNR reserving or predicting the number of IBNR claims, we even went to the daily level, right? So that's a bit the distinction I want to make here. You aggregate, but you aggregate on a very detailed time scale, right? And then you still use your ideas about calibrating models on this fine-grained data set and use it to forecast or to predict what's going to happen in the future. And next to that, you also have the idea of individual or case-by-case, if you want, or individual claims reserving. So what is the distinction between the two representations that we had higher up on the slide? So here I really mean we follow the development of an individual claim. So let's say from reporting on, and we try to work with the events that matter throughout the development of an individual claim over time. So we know that there is also a lot of work in that field. And I would say this is then typically done for the reported but not settled claims, so to predict the next steps in the future development of those claims. So I want to look at this literature on reserving from this perspective. And again, I want to see, okay, what can I get out of that literature on reserving that's going to help me to assist in completing those, in completing the incomplete information in my pricing data sets. I'll come to that idea later on. So here is, again, what I just mentioned. So if you look at aggregate reserving, I have chain ladder or GLMs kind of stuff into mind. I look at an aggregate data set. It's aggregated into a small sample data set, so I do quite a rough time discretization. If I look at granular reserving, I can look at aggregation, but aggregation on a very granular time scale, so into a large number of summary statistics. I would say that's what people have recently been working with in the field of nowcasting of IBNR claims. And then eventually we have this case-by-case reserving where we can use either machine learning methods or GLMs, but we can work there with the development of individual claims over time. So we try to work on that field as well. And here you have a few of our most recent papers. And I do mention them because I will use the ideas from these papers today and blend that with the pricing ideas that we discussed earlier on. So this is really a paper where we just try to bring different things we've been working on together, right? And in order to do so, I need two things. I need to think about predicting or being able to predict the unreported claims, because I said one of the problems in my pricing data set might be that I have an underreporting of the number of claims. And that can be relevant in a reinsurance case study because there you have a substantial time lag until reporting of the claim, because the claim has to become substantially large in order to get reported. So what we're going to do here is, if we look at this IBNR literature, the work that we did in our paper in statistical science, then we looked at a very fine-grained time scale, and we looked throughout the observation period that we follow in a portfolio of contracts, and we look at the occurrence of events and follow their delay until reporting, right? And you see what econometricians call a nowcasting problem coming up here. You want to predict the number of events which happened already in the past, but which are still to be reported in the future. But the idea that I develop in this typical reserving papers is that I follow the time period that comes with my portfolio of contracts, right? So I say, okay, I have contracts, I follow them between 2004 and 2015 or something, and I look at all the claims that occurred over all the contracts in my portfolio throughout that time, right? And here with the dashed lines, you see then the kind of discretization or aggregation that's typically going on here. So what you can do here, if you look at our work in statistical science, we really worked here at the daily timescale, in fact. So we did a very fine-grained occurrence period and reporting delay. You can then, you do the aggregation, and you can use your, you can use different types of predictive models in order to get an estimate of what should happen in the lower triangle. If you've never seen this, I think it's nice to look here at the connection between, for instance, what we're doing in actuarial science on this IBNR problem, but also what epidemiologists are doing when they look at the reporting of cases of a disease, for instance. So there are lots of similarities there. But of course, the epidemiologists, for instance, during a pandemic, they really need a detailed timescale because they really need an estimate of the daily number of cases, for instance, right? So that's where this fine-grained discretization becomes very relevant. Now, from our statistical science paper, the idea that I would like to launch right now, and which I'm going to recycle for the contribution that I present today, is the use of an occurrence and a development process, or an occurrence and a development model. So back in our research paper on IBNR reserving, we worked with, let's say, a Poisson model to model the number of claims that occur on a certain day t. And we say, okay, we're going to model that nt, the number of claims that occurred on day t or time period t, with a certain intensity where we can put in some covariates, but these covariates report or they correspond to the occurrence period that we're considering. So we want to know if it's a summer period or a winter period, if it's claims occurring on a Sunday or something. We can only use their information attached to the occurrence period t that we are considering. And that can be a day or it can be a week or something, depending on your time scale. And then in order to switch from the occurrence to the reporting, we're going to work with a well-specified reporting probability distribution, right? So we're going to say if we have nt claims occurred on day t, then ntd claims will be reported with a certain delay d, and I need reporting probabilities to manage or to model that reporting delay distribution. So that's what we worked on in that particular paper. We looked into the calibration of these models. We compared them with models established in the literature which don't do this decomposition, etc., etc. So the thing or the step that I want to take in this new paper is that here I use that occurrence and that development thing for a time period t in my portfolio horizon. So it's not at the level of a contract or a policy, it's at the level of a day in the time period that I consider, right? So the step that I want to take is, what if we're going to use this idea, but apply it at the level of an individual policy I, using the characteristics of that policy I, then we will be able to say something about the occurrence of claims with respect to that contract I and their reporting delay over time. And that may help me then to solve one of my two challenges in this incomplete pricing data set, namely that I'm facing an underreporting of the number of claims. And if I can do this occurrence and development, or this occurrence and reporting at the level of policy I, then that can help me to get an estimate of how many claims on this policy I do I still expect to be reported in the future, right? So that's the idea in terms of occurrence and reporting. But of course, beyond reporting, there is something else going on. That's the development of the claim over time. And of course, if we look at the literature on RBNS reserving, reported but not settlement, then one of the ways how we can handle that is we can look at the development of a claim since reporting. We can discretize the timeline from there in, let's say, yearly periods, whatever you like. And we can try to keep track of, okay, which events are going to happen throughout the development of a claim. Will there be a payment? If there is a payment, how much will it be? Will there be the settlement of the claim? This kind of things. So the way how I want to look at that is with an idea from, or a vision from individual claims reserving, but over discrete time periods, right? So I'm really gonna do some discretization, and I'm gonna keep track of, okay, what are the interesting events or the relevant events that happen in a certain discrete development period. And that's what we did in a recent IME paper with Jonas and with Jens, where we proposed what we call a hierarchical reserving model for these RBNS claims. So we're going to look at individual claims, we're going to look at development periods over time, and we're going to build a so-called modular or layered model. And many other contributions have worked along the same idea, so this is not that surprising or new. But the idea is that we can keep track of different pieces of information on claim K. So that can be static information. You know, for instance, the cause of the claim, or you know the initial incurred amount that was booked on this claim K, or you have some policy or policyholder covariates, things that don't change over time. And then you have information. We denote it here with U, and U is for updating, because you have information that updates throughout the claim's development over time. And this can be multi-layered, right? We can, for instance, be interested in the closing of the claim, so with a settlement indicator, 0, 1, that we follow for each claim K in each development period. We can be interested in, is there a payment, yes or no, with a payment indicator, and if there is a payment, what is the corresponding size? And this is typically, I would say, what you're essentially interested in for a very traditional non-life insurance portfolio. But if you step to a reinsurance portfolio, there might be additional layers that you can be interested in here. For instance, is there a change in the incurred amount? Is there a change in the incurred amount? And if there is a change, which is non-trivial, how much is that incurred amount being adjusted by the claims handler? So the idea of that layered approach is that you can extend the relevant pieces of information in those update vectors that you're interested in monitoring. So what do we do in this paper? We are going to build a predictive model for each of those layers, and you can do that with your favorite predictive modeling technique. And the idea here is that you can use, in order to predict for claim K in time period J, layer L, so let layer L be, will there be a settlement or not, for instance, or will there be a payment or not? What kind of information can you use then? Well, of course, the static information, which was available on this claim K from the beginning on. But what you can also use is previous information registered in the previous development periods of the claim. And you can also use information from the same time period, but from layers that you modeled earlier on. So that's typical, like if the claim settles, it often comes with a payment, for instance, so then you also want to take that piece of information into account. So we call that a time dynamic and layered hierarchical structure using both static as well as dynamic information. So why am I telling this? Because this is what's going to help us. If you look at my title, I have an occurrence and a development model for non-life claims. So this is what the development part is going to be driven by. So we're going to use this to model the development of our reinsurance claims in future time periods. And so here is a typical example of a basic setting that we study in our original paper. So what if you have a claim settlement indicator modeled with a Bernoulli assumption with a certain predictor in there using dynamic as well as static information? What if you have a payment indicator, again driven by Bernoulli distribution? And what if you have a payment size model, for instance, with a gamma distribution using that dynamic and static information? So that was my very long introduction. So I took you on a tour from the ideas of technical pricing for non-life insurance. I said there, yeah, maybe there is a problem there in the data set that you have available. You may have underreporting of the number of claims on a contract, and you may have claim sizes which are right-censored, right? And so how are you going to use as a pricing actuary that incomplete data set? And then I took you to the reserving literature where I said, yeah, if you look at IBNR modeling, we work with a timeline there that captures the observation period in my portfolio, and we try to use techniques there, either in, let's say, larger time periods or very detailed time periods. We use that to predict, to nowcast the number of claims at the level of the portfolio. And we use for the further development of reported claims, we can use that hierarchical or layered structure. So now we're going to bring, or try to bring, these two ideas together. And the original name we have in our title is Bridging the Insurance Pricing and Reserving Literature, but I feel like for the revision, I feel like we don't actually bridge, but we do try to combine the ideas in a clever way. So I'm still in doubt about, well, the specific title that we should use for this idea. But what are we going to do? So we want to think about that inconsistencies between actual observations in a severity data set and best estimates in pricing data sets. So we want to think about along that idea. We want to model both the occurrence and the development of claims, use the combined model for both pricing and reserving. So I want to do a single thing that can help me then for both tasks, right? That's the idea. And I want to demonstrate this occurrence and development model on a case study from reinsurance. Why from reinsurance? Because we think there it really matters, but right now, for the revision of the paper, we also calibrated this idea on a quite regular insurance data set. So I think eventually in the paper, we're going to do applications from both reinsurance and from regular insurance portfolios. So what is the change that I will make in my occurrence model? That I'm now going to specify that thing which we explored in the statistical science paper. I'm going to explore it, I'm going to define it at the level of an individual contract I. So instead of working with the TD dimension, where T was running over time in my portfolio, I'm now going to switch to an individual contract I. So I say NI is the number of claims occurring on that contract I. We have a certain intensity, lambda I, which can be function of certain policy characteristics. And once I have that NI occurred claims, I'm going to calibrate this well-defined reporting probability distribution in order to manage or to get grip on the reporting of those claims over time. What will that bring me? It will allow me, along that ideas that we develop in IBNR reserving, it will allow me to get an assessment of the number of unreported claims at policy level I in a data-driven way. So it will help me to say something about how many in the frequency component, how many claims do I think are still missing because they are not yet reported. That's the occurrence part. What about the development part? And there we're going to stick to that hierarchical reserving model that I just mentioned. But again, I, of course, need to make it very tailored to the kind of case study or to the kind of portfolio that I'm looking into. So for instance, if I do this with reinsurance, then I will also look, for instance, at changes in the incurred amount and need to specify layers to handle that as well. Yeah? So we can put this occurrence and development model together, and we can then do both pricing and reserving, or develop pricing and reserving ideas within that framework, let's say. So if we look at pricing, we can adjust our claim frequency data for unreported claims. And if we look at the claim severities, We can do two things. We can either simulate ultimate claim sizes from ground up, so imagining that no part has been developed or reported yet, or we can do for those, I have to stand here and stop walking around, or I can simulate paths of the future development of my open claims and use them then when fitting a severity distribution in my pricing model by really making a distinction between the actual observations. So here are actual observations, so they will really get a contribution at the density that I want to calibrate in my severity component of the pricing model, so that density evaluated in the actual observation. But if this is an open claim, I really want to use my observations for the ultimate, or my estimates, my simulated values for the ultimate claim amount. I really want to treat them differently, and I will say if I simulated n of them, I'll just give each of them a weight 1 over n or something. What is the difference with one of the pre-processing steps that I mentioned earlier on? Then you would first take the best estimate, so you would first do the averaging over all the scenarios that you generated, and then treat that as an actual observation in the likelihood when you calibrate the severity model. So we really want to see what is the influence of that practice, or what happens, or how does it influence your severity distribution if you really disentangle between the actual observations and the paths that you generate for the right-censored severity observations. And you see that being pictured here. So we have observed the development of a claim up to here. And then the only thing we can do, or the best thing we can do, is say, here I have 100 paths of what it potentially can be along our development model. And I'm going to acknowledge that these are just paths of what it can be in the future. I must say that, so we recently became aware that Hans-Jörg and Martin also have work in this field with the difference between actual observations and then scenarios for ultimate claim amounts. So that's some work that we still have to explore to see what is the difference here, or what are the similarities with what we propose. Right, so let me use another 5 minutes or something to just quickly give you the ideas from the case study, and then I'm going to wrap up. I think this is a nice data set. So it's a data set that hasn't been explored in the literature yet. It's a Belgian MTPL reinsurance data set. You see there a number of large motor insurance claims over a certain historical period. We have their detailed development. Those claims were reported by 21 underlying main insurance companies. We don't have many details about the clients, if you want, or the policyholders I in our data set. We just know their exposure as a kind of number of vehicles covered by company I in a certain year. And we also know what the reporting priority was that was put into place for these different companies. So the priority above which they would report the claim to the reinsurer. If the incurred amount set by the claim handler would be above that priority, then the claim would be reported to the reinsurance company. And then for each claim, we know details about when did it happen, when was it exceeding that priority, reporting priority, when was it settled, if it's already settled. And we also know the evolution of paid and incurred amount in every development year since reporting. So this is a bit peculiar and making the story perhaps a bit difficult. But I'm going to treat those insurance companies as my policies in my occurrence and development model, right? And reporting for me now means the claim exceeds the reporting priority. So it's a bit of a different kind of reporting than what we're used to when we look at main insurance companies. What do we want to do? We want to look at, let's say, excess of loss contracts, do pricing for those contracts, and reserving with that same occurrence and development model that I presented today. We can calibrate the occurrence intensity We can calibrate the reporting delay distribution. So the occurrence intensity here, it only takes, well, it's a lambda that is specific to the client, to the insurance portfolio that I'm considering. So what do you see? That there are few companies which seem to have like a sort of, well, a higher regime, so more claims occurring per unit of exposure than a few others of these companies. And we see differences, of course, in the reporting delay distribution, which can have to do with differences in how these claim handlers set the incurred amounts within these different insurance companies, differences that can have to do with the composition. Well, that's differences in the occurrences, then differences with the composition of the underlying group of vehicles that the company covers. There might be vehicles which are way more heavy, more buses, more trucks or something for some companies compared to others. So that was for occurrence and development. If you look at the development of claims, here, of course, the challenge is that you have quite a few things that can happen. We have settlement, we have payments, and we have changes in the incurred, right? So that requires us to distinguish quite a few possible layers in the development model. So what can you find in the paper? Well, we're going to explore gradient boosting machines for each of those layers. So will there be a payment? Will there be a settlement? Will there be a change in incurred? And we juggle around with the kind of covariates that we can use there, dynamic, static, and how that works. So we do, well, we have the details of that in the working paper. We also show with PDP plots how then these different components or these different predictions for the layers, how they change depending on some marginal feature effects. And I think we're much, or if you look at the ideas, we're much in line here with recent work by Professor De Long, Lindholm, and Wüthrich, who also worked with reinsurance reserving case study here. We can do the pricing then of these reinsurance contracts. We can look at differences in the calibrated severity distributions. If you treat the, well, if you make that distinction between simulated paths versus treating best estimates for open claims, so you really see that it makes a difference, right? And we quantify that in our paper. And we can do the reserving on that, on that portfolio of reinsurance contracts, and we also show the results of that reserving model with some out-of-time evaluations. Yeah. So that's a bit the idea. So we're still working on, well, on everything in this paper, but particularly also on the case study, where we now beyond the case study in the reserving. In the reinsurance case, we also want to do it with a more traditional insurance data set. Right, yeah, thank you for your attention, and thank you, Xavier, for putting everything here together. So that was what I wanted to share today. Thank you for being here and for listening.